Hello, welcome to Vast Diversity. Today we're going to be with limits at infinity. Last time we did continuity and intermediate value theorem, and so let's go ahead and finish up with the limits here. So we're going to take a look at a function f of x, which is equal to x squared minus 1 divided by x squared plus 1. Okay, so if we decide to graph it, the graph is going to look like the following, right? So as you can notice, if we decide to approach, to positive infinity, which is going to be here on the right side, positive infinity, or negative infinity on the left side, right? In both cases, we're going to be approaching a horizontal asymptote of y equal to 1. Okay, so that gives us an idea, right? An idea of the limit. So intuitive definition of the limit at the infinity, right? When x is approaching infinity. So let f be a function defined in some interval from a to infinity. Then the limit of f of x as x approaches infinity is equal to L. Means that the values of f of x can be made arbitrarily close to L by requiring x to be sufficiently large. All right, perfect. So we can have multiple ways of graphing such, right? So let's take a look at some of them, some of the popular ones, right? Some of the very common ones. So here's going to be an example. Right, let's do it side by side here. So we have that we can have something like this, right? We eventually going to be approaching infinity. Then we have something as an exponential function, and then some of the oscillations, right? And as we go to the oscillations, we will reach the desired value. All right, perfect. So now let's do same definition, right? But for the negative infinity. So for the negative infinity, right? Let f be a function that is also defined in some interval from negative infinity to a. Then limit of f of x as x approaches negative infinity is equal to L. Means that the values of f of x can be made arbitrarily close to L by requiring x to be sufficiently negative, right? Large in the negative direction. So, okay. Now it's going to be, essentially same thing as the previous graphs, but in the opposite direction, right? So now we are approaching negative infinity, right? As we're approaching negative infinity, we're approaching some horizontal asymptote, right? And so, well, now let's go ahead and define horizontal asymptote. So a horizontal asymptote is the line y equal to L, and it's called horizontal asymptote of the curve y equal to f of x. If either limit as f of x as x approaches infinity is equal to L, or limit of f of x as x approaches negative infinity is equal to L. Right, so for instance, our first example was that the limit for both sides, infinity and negative infinity, was approaching to 1. Right, what other functions have limits? So one of the famous functions is, of course, tangent, right? Tangent will have, inverse tangent will have the horizontal asymptote, right? So as an example, right, for horizontal for the inverse of a tangent, right, it's going to be negative pi over 2 and pi over 2. And of course, the graph of it will be as following. So this is going to be the graph of it. Okay, right, so if we're approaching positive infinity, we're going to go to pi over 2, and negative infinity is going to be negative pi over 2. So that is similar to what we do when we work with the regular tangent, right? For the regular tangent, if we're approaching the 90 degrees, right, for 90 degrees, the tangent goes to pi over 2, right? But if we go to 270 degrees, or negative, right, 90, we're going to go to, negative, we're going to go to negative pi over 2. Alrighty, perfect. So let's go ahead and talk a little bit about a theorem. So a theorem for the functions that are approaches essentially 0, right? So we have a lot of hyperbolas in those cases, right? So for the hyperbolas, we can have a theorem. So if r is greater than 0, so if the power of x is greater than 0, and it's a rational number, then the limit of 1 over x to the power of r as x approaches infinity is equal to 0. And if r is greater than 0 is a rational number such that x of r is defined for all x, then 1 over x to the power of r as x approaches negative infinity also approaches 0, right? So 0 will be horizontal asymptote for this kind of functions, for the hyperbolas, right? And that makes sense. Our most famous hyperbola and most famous function in general is 1 over x. Okay, so this is how it is, and we clearly see that 0 is the horizontal asymptote. Meanwhile, the vertical asymptote of that function is going to be y. We have done multiple asymptotes like that, right, back in algebra. So let's take a look at an example, right? Let's go ahead and solve an example. So it's going to be example 1. So if we have limit as x approaches infinity of 3x squared minus x minus 2 divided by 5x squared plus 4x plus 1. Okay, so the way we can do that, well, we see that we have x squared, and x squared is the highest power. Let's go ahead and divide the numerator and denominator by x squared. So we're going to have limit as x approaches infinity of 3x squared minus x minus 2 divided by x squared, okay, and then divided by 5x squared plus 4x plus 1 divided by x squared. So we're going to divide each term, right, each term by x squared. So what are we going to have? We're going to have the limit as x approaches infinity of 3 minus 1 over x plus minus 2 over x squared divided by 5 plus 4 over x plus 1 over x squared. So as we approach infinity, right, by the laws of the limit, we know that this is going to go to 0, this is going to go to 0, and this is going to go. So we're only going to left with 3 over 5. So and that's going to be our asymptote, right? Our horizontal asymptote for this function. And if we decide to graph this function, we actually indeed will get that our asymptote, horizontal asymptote is 0.6, which is the same thing as 3 over 5. All right, perfect. So we can do that for any of the limits, especially if we have rational limits, we can find the horizontal asymptote as we approach to the infinity. All right, so now let's go ahead and give a precise definition of the limit at infinity. Okay, perfect. So we will have that let f be a function defined on some interval from a to infinity. Then limit of f of x is equal to L means that for every epsilon, there is corresponding number n such that if x is greater than n, then f of x minus L is less than epsilon. Alrighty. Perfect. So, okay, now let's go ahead and take a look at it. Graphically. So here it is. Remember the definition of limits, so we will have the following graph, right? So we're trying to decrease this range with our epsilon, so we have to control of the epsilon such that we can be closer and closer to the function. So as we decreasing, right, as we essentially choosing smaller epsilon, we get a smaller interval here, smaller range, so we become closer and closer to the asymptote, right? So we decreased it in size. So eventually, eventually, right, we'll be able to reach it. So same thing we can do for the limit, right? The official precise definition for the limit to the negative infinity, right? Let f be a function defined in some interval from negative infinity to a. Then limit of f of x as x approaches negative infinity is going to be equal to L, means that for every epsilon greater than 0, there is corresponding number n, such that if x is less than n, then f of x minus L is less than epsilon. Alrighty, so that's how it's going to look like, but now we're going to the left side. Alright, perfect. So we can use that definition, right, to properly calculate the limit. And then, let's go ahead and do the final definition of the limit at the infinity, right? Because sometimes not all limits have horizontal asymptotes. Sometimes we might be going out of the asymptote. So the last definition for today is going to be definition of the limit at infinity. So let f be a function defined on some interval from a to infinity. Then limit of f of x as x approaches infinity is equal to infinity, means that for every positive m, there is a corresponding positive number n, such that for if x is greater than n, then f of x will always be greater than m. Right, this is an example, right? Like a parabola. If you think about a parabola, we're always going to be greater, right? Greater than the next. We will be able to find a greater number, and then the greater number, and then the greater number. And that's always going to be the infinity. Right, and for example, we do the same thing for the negative infinity. And, for example, would be a negative x squared. All right, so that essentially concludes the limits at infinity. Thank you, guys. And next time, we're going to start the derivatives.